Assalamualaikum dear students. This is our lecture number 21 of topology. Once again, we want to start the rest of the syllabus. So today I am going to define the concept of a continuous function in a topology. So before giving the definition of a continuous function, we need to understand continuity at a point. So let's have the definition. Suppose x tau x and y tau y be two topological spaces. A function f from x to y is said to be continuous at a point x naught of x. Just like real analysis, you take a point x naught of x and you define a function from x to y. But here the definition is a little different than real analysis, as we have defined in real analysis. If for any neighborhood, I am using this symbol NBHD instead of neighborhood, I will write a neighborhood like this. So if for any neighborhood V of fx naught in y, there is a neighborhood U of x naught in x, such that fx naught belong to f of u, which is contained in V. Okay, if this is the case, then we will say that our function is continuous at x naught. So the idea is you have, this is your x, it's a topological space x, you have a topology on here, tau x is a topology on x, and you have another space y, and it's a topology tau y. Suppose we have two topological spaces and you take a point x naught of x, this is x naught. Naturally, if you are defining a function from x to y, you say you have a function f from x to y. So certainly this number is here, must be fx naught, right? X is mapped onto fx naught. X tau x is a topological space, y tau y is another topological space. You take a point, you want to define a function from x to y, and take a point x naught of x, certainly under f, its image is fx naught. Now the idea is, take at a point x naught of x, if for any neighborhood V of fx naught, suppose you have a neighborhood V, this is your neighborhood V of fx naught, you have a neighborhood here in y of fx naught. Whether this neighborhood is open or closed, this time till now I am not concerned, right? You just you are taking just a neighborhood of fx naught. Fx naught is the image of x naught, and you are taking V. V is a neighborhood of fx naught. So corresponding to any neighborhood, you know, here V is not a fixed neighborhood. You may have more than one neighborhoods of fx naught. You may have a neighborhood family of fx naught. You may have many neighborhoods v1, v2, v3, v4 of fx naught. That's why we are saying for any. This word is very important. For any, whatever the neighborhood you are choosing, which is neighborhood of fx naught, so better to list all the neighborhoods of fx naught. Suppose you have fx naught and you have taken all the neighborhoods of fx naught in tau y, right? Here in y. So function is continuous at a point x naught of x if for any neighborhood v of fx naught in y, there is a neighborhood u of x naught. This means that corresponding to this neighborhood v, there must be a neighborhood u of x naught. The idea is You take x naught, then take its image fx naught, then find a neighborhood of this point fx naught. If V is a neighborhood of fx naught, then there must be a neighborhood U of x naught such that fx naught belong to f of u, which is contained in V. So its image set, the image set of U is in fact here in the neighborhood of V. This is your f of u. The idea is, now listen again. We are saying that a function f is continuous at a point x naught. You take x naught, and then of course you have its image fx naught. Of course, this image is in y, and then find a neighborhood v. If v is a neighborhood of fx naught in y, then there must be a neighborhood u of x naught such that the image set of this neighborhood is also contained in V. If this is the case, then we will say that function is continuous. So what should be the working rule? You take a point, you want to check the continuity at x naught, find its image, which is fx naught, and then find all neighborhoods of fx naught in y, and then corresponding to every neighborhood, you must get some neighborhood u in x so that f of u is contained in V. And if this is happening corresponding to every neighborhood of V of fx naught, then we will say that this function is continuous. Okay, this is in fact the basic idea of continuity at a point. We will try to develop a more better definition through this definition in terms of theorems, right? Which would be easy to apply on your questions or examples. Because anyways, this is the basic definition. The definition is, I can once again tell you, you have a point fx naught here in y, and corresponding to this fx naught, we will find a neighborhood V, right? If you take a neighborhood V of this fx naught, there must be a neighborhood U of x naught so that its image set must be here in, this is f of u, right? So this was first topological space, this was second topological space, and in this case we will say that our function is continuous. So see, I write this another way. Okay, this is your first topological space, this is x, and this one is y, this one is y. You take a point x naught, you want to define a function from x to y. Of course, on this set you have tau x as topology, on this set you have tau y as topology, and we want to define continuity at a point x naught. So certainly if f is a function from x to y, then under x naught here is the image fx naught. The idea is we will find a neighborhood of fx naught in y. Suppose you have this neighborhood V. So V is a neighborhood of fx naught in y. What is this? V is a neighborhood of fx naught in y. So first you will find a neighborhood V of fx naught in y. Whenever you find a neighborhood V of fx naught in y, there must be a neighborhood. There must be a neighborhood U. There must be a neighborhood U. This means there must be a neighborhood U of x naught in x such that if you find its image set, then its image set is in fact here. Its image set is in V. So if this is f of u, means that here f of u is a subset of V. Right. And this is not for one neighborhood of fx naught. If you can find a neighborhood in x corresponding to every neighborhood v of fx naught, then we will say that our function is continuous. So like we can discuss with the help of some examples. So when function is not continuous, of course, the idea must be here fx naught, this is your y, and fx naught, this is the neighborhood of v of fx naught. And if your u is here like this is your f of u. If this is your f of u corresponding to, of course, you have some x naught, and this is your u neighborhood, but the image set is this. This is the image set. Then we will say that our function is not continuous. So continuity says that if you are finding some neighborhood v of fx naught, then that neighborhood will contain, then there must be even so small, we are not concerned. I am not saying that every neighborhood of x naught should be in V. No, I am not saying this. I am saying this, that there must be at least one neighborhood. There must be at least one neighborhood u of x naught. There must be at least one neighborhood u of x naught, such that the image set of f of u is contained in V. And now if this is the case, you are not getting even a single neighborhood u of x naught, so that f of u is not fully contained in V, then we will say that this function is not continuous, right? So this is the definition. So whenever you need to check, you choose neighborhoods of fx naught, and then turn by turn check all the neighborhoods. Means say that if you have, suppose if you have v1, v2 and v3, three neighborhoods of fx naught, then you have to check whether for v1 you are getting some u1, and for v2 you are getting some u2, and for v3 you are getting some u3, so that the condition that f of ui is contained in vi is satisfied. If this is the case, then we will say that our function is continuous. So let's do this with the help of examples. Okay. So suppose I choose x is equal to a, b, c, and I have tau x is equal to phi x. You can take a, c, then a, b, then a, c. This is my x, and tau x, then you take y is equal to 1, 2, 3, and tau y is equal to, say, I am choosing phi y and 1 and 1, 2. Say these are the sets x and y, and I have chosen two topologies. Say x is equal to ABC and tau x is topology. You can check that a union of AC is here, and intersection of this and this is equal to A is here. Yes, this is a topology, right? And also y is equal to 1, 2, 3. If y is equal to phi y 1 and 1, 2, yes, it is a topology. So I have two topologies. Now define a function f from x to y. Define f from x to y by f of a is equal to 1, f of b is equal to 2, and f of c is equal to 3. Okay, so this is our question. You are given this function, you are given the definition of f, you are given x, you are given y, you are given tau x, you are given tau y. Now you need to check that with respect to our previous definition whether this function is a continuous function or not. So you have to check for a, then for b, for c, because function is from x to y, and x has 3 points a, b, c. So that's why I need to check turn by turn. I need to check first for x is equal to a. Okay. To check continuity, uh, to check continuity at x is equal to a. Okay, first we will check continuity at x is equal to a. Note that what is f of a? So f of a was given. This is 1, and what was the definition? Find the neighborhoods of fx naught. Your x naught is equal to, in fact, this is your x naught. When x naught is equal to a, this is your fx naught is 1 and 1. Find the neighborhoods of 1 in tau y, because you are taking function from x to y. So neighborhoods of f of a, that was 1 in y. So then neighborhoods, so I am writing NBH DS for neighborhoods. Neighborhoods of f of a is equal to 1 in y are, what are the neighbors? Look at here. One is contained in here, one is contained in here, and one is also a member of y. So you have 3 neighborhoods. So one is v1, which is equal to 1, and then v2, which is equal to 1, 2, and then v3, which is equal to y. Okay, the first idea, choose a point, find its image. That is, now you are in y set, you are here, and then find its neighborhoods. So second idea is corresponding to every neighborhood. You must have some neighborhood in x, so that that is u, say. You must have some u and neighborhood in x such that f of u is contained in v, right? So that's why I will check for v1 and for v2 and for v3 separately. If you can choose even a single neighborhood in x which satisfy the definition, then this means that function is continuous. And at that point, if the definition is true for all these 3 neighborhoods. So that's why first, if for take v1 and we choose okay, it's better to find you can already see the neighborhoods of a, because we are finding the continuity at a. So that's why you should have neighborhoods of a in x. So here a, ab, ac, and then x. There are 4 neighborhoods. So I am not saying that these 4 would survive. If one of them is satisfied for your v1, then we will leave v1. This means that v1 is satisfying that desired condition, right? So that's why you can choose. We can choose. We choose u1 is equal to a. Yes, this is the neighborhood of a, because we are finding the continuity at f of a. So that's why you need to find a neighborhood of a. So you can list already before writing this, you can, like I have listed the neighborhoods of 1 in y, then also you can list neighborhoods of a in x here, and from those neighborhoods you choose as per your convenience, right? So we choose u1 is equal to a, right? Then you see f of u1 is contained in v1. So what is f of u1? Then f of u1 is equal to f of a, right? This is equal to f of a. Your u1 was a, which is equal to f of a, and this is equal to, in fact, this is 1, and which is contained in v1, right? This is 1 and which is contained in v1. So this means that corresponding v1 you have a neighborhood u1, right, which is serving the definition that f of u1 is contained in v1. And similarly, you will check whether for v2 you can find some u2 and v3 you can find some u3. If this is the case, this means that your function is continued at x is equal to a, right? So you can choose all the neighborhoods of a first. Then you can write all the neighborhoods of a. Then from those neighborhoods you can choose as per convenience so that the definition is satisfied. Like again, you see, we know the definition. The definition is a to 1, b to 2, c to 3, right? So again, at x is equal to a, I want to check continuity at x is equal to a. Find the neighborhoods of f of x in y. Then note f of a is equal to 1 and neighborhoods of f of a is equal to 1 in y are, you have 3. Here we have 3 neighborhoods. One is v1 is equal to 1, v2 is equal to 1, 2, and v3 is equal to y, right? Similarly, you can write neighborhoods also, neighborhoods of a in x are, what are these? You have u1, u2, u3, u4. You have 4 neighborhoods. So u1 is equal to a, u2 is equal to ab, u3 is equal to ac, and u4 is equal to x. Right? We have 4 neighborhoods. Okay, now you need to take any of these 4 for v1 to satisfy the definition. If you can find any of these 4 for this v1 that satisfy the definition, this means that for v1 you have a neighborhood. And similarly for v2, you have to find whether there is a neighborhood which satisfies the definition. Similarly for v3, you have to find whether there is a neighborhood which satisfies the definition. If this is the case for all v1, v2, v3, if for v1, v2, v3, you can find some neighborhoods from these u1, u2, u3, u4 so that the definition is satisfied, then we will say that function is continuous at x is equal to a, right? Okay, so for v1, we can choose, so you need to be a little clever because you know v1 is 1 and which one you can choose? You can choose u1 because f of u1 is f of a, this is 1 and 1 is contained 1. You cannot choose u2 because if you will choose u2, then f of u2, basically f of ab, which is 1, 2, which is not contained in v1. So you should not choose u2 or u3 or u4. You can choose u1. right? So for V1 you have only one choice, that is U1. That's why. Anyways, you have the definition. The definition is satisfied. That's why we will leave V1. Then for V2 we will discuss V2. So we can choose U1 is equal to A, so that f of U1, which is equal to f of A, this is equal to 1, which is contained in V1. Of course, this was V1 and every set is contained in itself. So the definition f of U1 is contained in V1 is satisfied. That is f of U1 is contained in V1 is satisfied. I'm not saying that every neighborhood UI should satisfy the definition for V1. No. We are saying that if for every neighborhood of fx naught, you can find some neighborhood of x naught in capital X, so that this condition is satisfied, then we will say that function is continuous at x naught, right? Okay, so for V1 the condition is satisfied. For V2, it is very clear that V2 is equal to 1, 2. So which neighborhoods can survive? U1 can survive, U2 can survive, right? So for V2 we can choose U1 is equal to A and even U2 is equal to AB, so that f of U1, see, f of U1, you already know that this is in fact 1 is contained in V2. Yes, 1 is contained in V2. This is contained in V2 and f of U2. What is f of U2? U2 is equal to AB and f of U2 is equal to 1, 2. And 1, 2 is contained in V2. Yes, this one is satisfied. FU2 is contained in V2. What is FU2? F of U2. U2 is AB and f of U2 is equal to 1, 2. And 1, 2 is contained in V2 because V2 is 1, 2. That's why both you can choose U1 as well as you can use U2. So, but we are not required to find more than one. We are required to find just one. So, if you take U1 and U1 is surviving, that's why the definition is satisfied, right? But somehow I am showing that you can choose U1 and you can choose U2 as well, so that the definition is satisfied. So here you have two options. Similarly, for V3, we can choose, okay, what is V3? V3 is Y. Y is 1, 2, 3. So that's why you can choose U1, you can choose U2, you can choose U3, you can choose U4. You all can be chosen, right? So we can choose, I'm saying for V3 here, so what I am saying for V3, we can choose U1, U2, U3 and U4 also, so that you see what is f of U1? F of U1, what was U1? U1 is A and f of U1 is 1 and what is contained in V3? Your V3 was Y. Your V3 was Y. Here V3 was Y, right? So the third neighborhood of f of 1. This was f of 1. This was V3. This was V3. This was V1 and this was V2 and this was V3, right? So this was V3, this was V2, and this was V2, right? So since V3 is equal to Y, that's why f of U1, this is equal to 1 and contained in V3. Similarly, f of U2, which will give you, and U2 is here, this is AB, this will give you 1, 2, this is also contained in V3, right? Similarly, and then f of U3, what was this? F of U3 is AC, this was AC, so this is 1, 3, this is also contained in V3, and f of U4, this is equal to, in fact, f of x, which was y, which is also contained in V3. You see, I am not saying that you have to show more than one. If you can find just one, just U1, which satisfy the definition, then this means that function is continuous at that particular point, corresponding to every neighborhood. If you can find a neighborhood U of x naught in x corresponding to every neighborhood, means say that if for every neighborhood V of fx naught, there is a neighborhood, there is some neighborhood U of x naught, so that f of u is contained in V, then we say that our function is continuous at x naught, right? Hence f is continuous at x is equal to a. Now we will check continuity at x is equal to b. Then we will check continuity at x is equal to c. Okay. Now at b, at x is equal to b, continuity at x is equal to b. So note that f of b is equal to 2 and neighborhoods of 2 f of b is equal to in y are, look, find the neighborhoods of f of b, that is 2 in y. You see here, here are two. One is v2 and the other is v3. You have only two, v2 and v3. So you can label again, don't need to write this v1, v2, v3. So these are the neighborhoods. So here neighborhood 2 are, one is this v1 and one is this v2. I am saying this is v2, this is v1 because I am finding the continuity at b. So that's why I am reassigning the symbols. This is now v1, this is v2. So we have just two neighborhoods of 2. So every in y are, one is v1 which is equal to 1, 2 and the other is v2 which is equal to y. Again we will find the neighborhoods of b in tau x. Now also neighborhoods of b in x are, what are the neighborhood of b? One is AB and second is x. You have just two neighborhoods. One is u1 which is equal to AB and u2 which is equal to x. Again, for every neighborhood v of f of b, can one of these survive to satisfy the definition? We will check. So you have to check corresponding to every v1, v2, v3, whatever. Okay. So for V1 this is equal to 1 2, we can choose U1 is equal to AB, so that you see f of U1 which is equal to, in fact f of AB which is equal to 1 2, in fact this is V1 which contains V1. Yes, the definition satisfied. So you can also choose, you cannot choose U2. You cannot choose U2 because U2 is not surviving. So anyways, we are not required all the neighborhoods. We require just one. So that's why you have U1. That's why the definition satisfied. Now leave this. Now for V2, which was your Y, we can choose both. U1 will survive because 1 2 is a subset of Y, and if you take X, then f of X is equal to Y, which is a subset of Y. So both are surviving. So you can choose both, right? We can choose U1 and U2 as well, so that f of U1 is equal to, what is this? This is f of AB. What is this? This is equal to 1 2, and 1 2 is subset of Y, which is a subset of Y, which was V2. Yes, the definition satisfied. For V2, you are finding U1. U1 is surviving. U1 is working for both. And also, you see f of U2, this was f of Y, and you know that what is f of Y? Sorry, U2 was X. U2 was X. U2 was X, this is f of X, and this is equal to Y by definition, and Y is a subset of Y, and which was V2. Yes. So for V2, you also have U3, so that f of U3 is a subset of V2. So that's why for both the neighborhoods, you have some neighborhood in X which satisfy the definition. This means that function is continuous at X is equal to B. Hence f is continuous at X is equal to B. Now we will check for X is equal to C. Hence f is continuous at X is equal to B. Similarly, you can check for X is equal to C. The definition would be satisfied. Continuity at X is equal to C. Okay. Again, continuity X is equal to C. You see what is f of C? This is equal to 3. So neighbors of f of C is equal to 3 in Y are. Here is only one neighborhood. That is your that is Y, because this one is not containing 3. There is no 3. So 3 is an element of Y only. So you have only one. That is V. So and neighborhood of f of C in Y is just V. V is equal to Y. Now, can you find some neighborhood U of C in X so that f of U is a subset of V? We will see. So also neighborhoods of C in X are, you can see, have AC, say this is U1, and also C, you have three. One is u1 is equal to c, u2 is equal to ac, and u3 is equal to x. So you can choose all three that will that would survive. All three would survive, right? So for v is equal to y, we can choose u1, u2, and u3 so that you see what is f of u1. So u1 is c and f of u1 is 3. That is 3, and you know this is a subset of y. Yes, this one is satisfied. So till here you can say that f is continuous. No need to check u2 and u3. Just for sake of your convenience, I am checking that u2 and u3 also serving to satisfy the definition. There is no need to check for u2 and u3 once you find you found u1. So since u1 is satisfied, u1 serving the definition, that's why we don't have any need to check u2 and u3. Anyways, this is information. This is in fact additional information for you, that you have two more neighborhoods, u2 and u3, which are also satisfying the definition. So here also f of u2, what is u2? So u2 is AC. So here this will be 1, 3. This is also subset of y, which was your v, and f of u3, which is f of x, which is y, which is subset of y, which is equal to v. So f u3 is also satisfied the definition. Hence, this means that your function is, this function is continuous at x is equal to c. And if a function is continuous at all the points of the domain, then we call that this function is continuous, right? Okay, so the definition is hence f is continuous on x. That we say that f is continuous on a set x if f is continuous at each of its points. Since f was continuous on x is equal to a, and x is equal to b, and x is equal to c, that's why you can say that f is continuous at x, right? However, if you define its another function g from y to x with the same topological spaces, this is not the case that that function is also continuous. So define another function, define g from y to x by g of 1 is equal to a, g of 2 is equal to b, and g of 3 is equal to c. Now you have to check whether this g function is continuous. Suppose I have defined a new function from g y to x, where for y you have this topology, and for x you have this topology, and these are the two topological spaces, and corresponding to this function I want to check whether this function is continuous or not, right? So we have to check again using the definition. That what was the definition? That if you take some 1, then find g of 1, which is a, then find all the neighborhoods of a in x, and corresponding to every neighborhood, if you can find some neighborhood in y, so that f of u is contained in v, then we will say that it is continuous at x is equal to 1, right? So let's do this again. uh, continuity at x is equal to, sorry, now you can say that at y is equal to 1, because my first set is y, so its elements are small y, right? So y is equal to 1. So note that g of y, that is g of 1, is equal to a, and then the idea is find the neighborhoods of a in x in codomain. Find the neighborhoods of the image in codomain. Note that then neighborhoods of g of 1 is equal to a in x, which was codomain, in x are, what are the neighborhoods of a? You know, here a, ab, ac, and x. You have four neighborhoods. Or a, that is your v1, and ab, this is your v2, and ac, this is your v3, and x, this is your v4. So for a, you have four neighborhoods here in x, in your image set, right? But we have to check turn by turn whether corresponding to these all neighborhoods, corresponding to v1, v2, v3, v4, can you find a neighborhood of 1 in y, so that the definition is satisfied, right? So let's check. Also, neighborhoods of 1 in y are, which are, you have 1, 2, and 3. You have three neighborhoods. u1 is equal to 1, u2 is equal to 1, 2, and u3 is equal to your y. So rather to check v1, v2, v3, I can check v3 directly. You know that if I will take v3, you cannot find any of these because there is no element 3 is here in u1 or u2. But in u3, that would not satisfy that f of u is contained in v. So why not I check first v3, right? You can check. v1 will be satisfied, v2 will be satisfied, because corresponding to v1 you have u1, corresponding to v2 you have u2. But can you find corresponding to v3? No, this is not the case. I know that corresponding to v3 you will not have any of these neighborhoods which will satisfy the definition, right? So for v3, you cannot choose any. If you choose u1, this will survive. This will not survive. u1 will not survive. If we choose u1, then you see f of, for v3 you have to check g of v3, g of u1, that is equal to 1, okay. So u1, this is g of 1, this is g of 1, which is equal to a, and which is contained in v3, right? You see this u1 is you have to check that whether this one is satisfied, Okay, so this one is satisfied. I think we should check directly at C, because if you take C, then corresponding to C, you have no value here as 3 in this set. So this is satisfied. In fact, now I can check directly for y is equal to 3, right? If I check for y is equal to 3, okay, my definition was G, my definition was G1 was A, G2 was B, and G3 was C. Okay, check again for continuity at y is equal to 3. I need to check for y is equal to 3. Note that g of y, that is g of 3, which is equal to c, and neighborhoods of c in neighborhood of g of 3, which was c, in x are, what are these? One is c, and then you say this is v1, and then ac, you this v2, and then x, which is v3. Okay, also neighborhoods of 3 in y are here. You have only one neighborhood, this is y. You have only one neighborhood, this is y, because here I have no 3, so s in y is u is equal to y only. Now for v1, if you take v1, then it is very much clear that f of u, which is f of y, which is equal to x, is not contained in v1. So that's why the definition is not satisfied. So for v1, here is no neighborhood which is surviving. Also for v2, here is no neighborhood which is serving for the definition. That's why this function is not continuous at x is equal to c. Right? So for v1, if we choose u is equal to y, because you have one option, you have no other option to choose. That's why you have to choose y. U is equal to y. Then f of u, what is f of u? This is f of y. What is this? This is equal to x, g. Here your function is g. Your function is g of u, which is g of y, which is equal to x, and x is not contained in v1, which is not, what is x? X was a, b, c, which is not contained in c, which was your v1. Look at the calculation that gu is not contained in v1. That is, gu is not contained in v1. So corresponding to a neighborhood v1 of c, corresponding to a neighborhood v1 of g of 3, you cannot find any neighborhood of 3 in y which satisfy the definition. That's why g of u is not contained in v1, hence by definition this is not continuous. Hence by definition g is not continuous at x is equal to c. Okay. This definition is a little tricky, and this is not easy to apply. because you have to find the neighborhoods of f of x naught in y, and then you will find that corresponding to every neighborhood of your second set. Can you find a neighborhood in the first set so that the definition is satisfied? That's why this is a little tricky as well as a little lengthy. So people don't like this definition. Rather, this is the true definition. This is the actual definition of continuity. So in next lecture, we will use this definition to develop another definition, which is probably more friendly and easy to use. Uh, so that theorem, most of the author you used that definition, that whenever you have some open set corresponding to your f of x naught in y, its inverse image should be open in x. This is the simple definition and easy to use. But how you have established this definition, I'll try to elaborate in my next lecture. That the definition people are enjoying is in fact is a deduction, or you can say a major result of this definition, that I have used this to understand the continuity of these two examples. First was the continuous function, and the second function g from y to x was not continuous because it was not continuous at c. So in my next lecture, I shall show you that the definition people are enjoying and are using is in fact is a deduction of this definition. So this was the real and basic definition of continuity in topology. Okay, thank you very much. Allah Hafiz.